Okay, so as you can see, my name is Apurva Dhingra. I am a PhD student in IIT Bombay. I'm in my fourth year. I am working with Professor Ankur Kulkarni itself, and I'll be the PMRFTA for this course. So the name of the course is Stochastic Control and Communication. If you had a chance to go through the lectures, you would have noticed this is Ankur sir's version of understanding how stochastic control and communication can work together. So that's the framework that he's going to build in the course. Let's get started. So the first thing here is stochastic control. I've written a statement that stochastic control means decision making under uncertainty. In fact, these were the words that some of you also used. Can anyone explain what do you understand by them? What is decision making and what is uncertainty here?
Can I start off with an example?
Yeah, sure.
Yeah, so one of my final year statements, problem statement is that I have to generate an automotive scenario in uncertain scenarios like, in, let's say, unstructured environment in the Indian driving traffic scenarios. So in a traffic scenario in a closed campus, autonomous vehicle has to take a decision now, it has to overtake or not, right? So that is pretty uncertain and like at any point of time, if there is certain VRU coming in between, it has to stop the overtake maneuver. So that kind of a decision making in this kind of uncertain scenarios, I think this will be a problem for that. Like, I don't know if I'm correct or not, but I think that's what we're going through.
Fair enough. So the word decision making just means that there is some kind of choices from a set of choices, and one will be picked, or some plan will be made as to which one should be picked in which scenario. So decision making just refers to coming up with some choice. And the other word, uncertainty, means there is some randomness somewhere. That randomness could be, for example, in the example you gave, the other people in the traffic scenario, where are they going to turn? Is there going to be a random person who just is giving a signal for turning this side but ends up turning on the opposite side? So in such situations, how will you handle decision making? That's what comes under stochastic control. Okay, so this is some
Can I ask
randomness.
question in between?
Yes,
Is
just
it allowed?
remember, if you want to ask question, raise your hand.
Okay.
Yeah, but this time you can go on.
So even in the course, like sir was mentioning, set and it finite or something, I'm assuming, but it has to be finite or it can be infinite set. Countable infinite basically.
It can be infinite. It's just that infinite is something that's dealt differently from finite sets. Finite because we'll have a fixed number of decisions available, so you'll be able to solve them in a tabular manner. You'll be able to solve for each of them, so it's easier to handle. That's about it. The way to handle it in principle is same, but the process you might use or the algorithm you use would have differences because you have limited resources.
Resources in the sense?
Compute. So,
Only compute.
yeah, compute.
Okay.
There could be other ones, but let's take the simplest case, which would be compute.
Yeah, sure. Next time I'll raise the hand.
Yeah. So there are a lot of things that will happen. I am assuming they will come in the upcoming lectures. I don't want to start giving new words, but if you want to see this, in case of infinite space, if the decision or the state space, both of them are infinite, then there are processes like tile learning and stuff of that kind, TD learning and all that. But don't worry about that. We'll get to it hopefully in this course itself. All right. Any other questions?
No, not as of.
Okay, perfect.
Thank you.
Yeah. So I hope you all had a chance to at least go through the course plan. The course is structured in such a way that roughly the first 1/3 will be spent talking about what are called Markov decision processes. This is the standard formulation to deal with stochastic control problems. So this is part number 1. Then there'll be one particular portion where team theory type problems will be dealt with, meaning people are trying to work together and they may have some decentralization, as in they don't know everything about the environment. They don't have a central unit telling them what they should do. So in such scenarios, how should decision be made? And the third one is studying the communication aspect of all of this. This will require us to take the basics of information theory a little bit. And some of the examples, in fact several of the examples that will be dealt in this course will be coming from economics. But that doesn't mean they are restricted to economics. Same thing can be applied to planning. Same thing can be applied to multi-agent systems. So RL is a straightforward thing. It's the next thing that people do. Alright. Now, in stochastic control, there are two important aspects that need to be taken care of. So one of them is risk and the other is information. Risk is something that we have some intuitive understanding of. That if we are making, for example, an investment into something, we would want to be able to get some amount of returns. We would not want to see all of the investment we made going to nothing. So typically people want to minimize the risk in making an investment, for example. But even though we have an intuitive understanding of this, choosing the right framework to signify what risk is one of the things that was dealt in the lecture notes also, and I'll quickly revise all of that. The other aspect is of information, as in who knows what at what point of time. If the information available to any agent is changed, the problem pretty much changes. And if the problem itself has changed, then we can say that the further things that is happening in the problem, optimization or whatever is being minimized or maximized, will also be affected by it. In certain scenarios, information may not affect the final optimal value, but most of the times information plays a very important role. Alright, so the formal model that we saw was there is a set of decisions, and we're denoting that by this capital D. So any decision or any choice or any action, you can use any of these vocabularies, equally the same thing. So D belongs to the set capital D. Then this omega represents the set of states of nature. States of nature is where randomness or uncertainty will most likely be lying, or state of the world or state of nature. Either of those terms is the same thing. So we'll be representing that by mostly some omega. So omega lies in capital omega. Then we have this function, which is a function on the decision to be made and the state of the world. So based on these two, we get the outcome of any decision. So let's say the outcome is for decision D and state of the world omega. Now if we put all the possible outcomes together, we can put them in a set of outcomes. And finally, this symbol is not the same as normal equality inequality symbol. This refers to preference ordering, and the preference ordering is between outcomes or decisions. So if I say there is some θ1 that lies in O, and I denote it by this symbol, then it just means that it's θ2 that is the outcome that is more preferred. Okay, so now we will try and put our core understanding of risk in this model and take an example. Yes.
Yeah, I have set of questions.
Ask.
One is that in risk, we quantify the risk in the lecture, but information we treat as like something known. We are not quantifying mathematically. But as per my knowledge, we have mutual information concept where we try to quantify information. Are we going to use that?
So, as far as I am aware, typically people do not use measures like mutual information to talk about information gathering in control settings. It can be used, but here when we say communication or information, it refers to what is known to the agents.
Okay, but how do we quantify? Like agent A knows more than agent B,
Okay.
like something.
So I'll give you a couple of words. These are the things that people who study multi-agent systems or game theory, they study these. So there are models called Omen model.
Oh, okay, yes.
And there's one more. I am forgetting the name, sadly.
Yeah,
I can look it up and tell you next time.
Something. K of 1 and then something. Okay. That model.
So this gives you like how do you quantify what is the knowledge of one agent versus the other one, knowing what I know about the other one, what do I know about the whole thing. All of that is something that comes under Omen model.
Common knowledge.
Yeah, the common knowledge concept also comes here.
Okay. Perfect.
As far as I understand, this course will not deal with the details of what kind of information structure we're talking about. We will stop at just saying who knows what, and we'll just say it in words, and we'll stop at that.
Okay. And then second question was this f of d comma omega. Both are discrete and f is some function. Okay, which is I'm feeling O is also discrete because you are talking about finite set. So is also discrete.
Yeah, right
so now f mapping d comma omega to O, we are not talking about more the the characteristic of this function. For example, is it invertible or not? If somebody knows the output, can it go back to and take the information of state and decision made by agent or something? What are all this?
So right now we're not dealing with all of that. Eventually, in the upcoming weeks, when Sir defines what is an MDP, what is a state, what is a decision, like when things are defined slightly more carefully in a broader model of Markov decision process, then F might have a clearer meaning. Right now, it's just more like a labeling. So given D and W, what outcome does it get labeled to? That's about it. It's nothing more than that. And right now we're not focused on what kind of characteristic or properties this F is supposed to have.
Cool then. Thank you.
Yeah. Anyone else? Anything? Any other questions? Okay. Let's move forward then. I hope you've noted down this model. I am gonna erase it from here. I don't want to confuse the other people. Okay. Alright, so let's take the example that was taken in the lecture notes also. So let's say you can use 100 rupees to buy one cake. Or this is option number 1. Other option is you can enter a lottery. To enter the lottery, you'll have to pay something, and that amount, let's say, is the same. So it's still 100 rupees. What you get as the outcome of that lottery is you could get 3 cakes, and that comes with some probability. Let's say that's 2/3. These are the exact same numbers and the exact example from the lecture notes itself. And the other option is the outcome of the lottery could be getting 0 cakes, but this happens with a lesser probability of 1/3. Now let's put these things in the framework and see what is what. I'm sure you guys understand so far. So how about you answer? What are the decisions to be made in this problem? Let me give them some names and then you can answer. So let's say this is D0 and this is D1. Yeah. So what are the decision? What is the set of all decisions? The decision to be made here is the choices. So either to just buy the cake directly or get the lottery. So decision is just sorry.
Yeah, I was about to say that.
Oh, I should have waited a little longer. Go on.
Yeah, so two decision like you pay and take the one cake, or you pay for the lottery and make sure like, or maybe like risk for three cake.
Yeah, correct. So D refers to T0 and D1 here. Okay, that was the set of decisions. Now let's look at the set of states. Now, set of states is all the states. Let's give them some labels. Let me say in the first decision, just getting a cake in return for the money, let's call it W. This one I'm calling as W1 and W2. So what is this omega?
It's like 0 cake, 1 cake, 3 cake.
Those are the outcomes.
Okay.
So right now I'm not quantifying what the outcomes are. I'm just gonna write them in a symbolic form, but yes, otherwise, yeah, close enough. So W, W1 and W2. What you said are the outcomes. So let's just call it the number of cakes. So that's 1, 3 and 0. This is number of cakes. And since the outcomes are just numbers, number of something, the preference ordering is straightforward here. 3 cakes is more than 1 cake, 3 cakes is more than 0 cake and all of that. So there's nothing much that we can say here, that we need to say here about preference ordering. Okay, now let's write down what this F is in our particular example. So when D is D0, there's only one state of the world, and for that the outcome is 1 cake. When the decision is D1, there are two possibilities. Let me write it this way. So there can be either 3 cakes or 0 cakes, depending on which state of the world we are in. Okay, so I hope you can see, Manas, I believe, that F is just acting as some sort of a label here and nothing more than that. Is that a question? So Prabha, is there a question? Okay. All right, let's continue. So in this particular scenario, what would be preferred to do? Are we going to take decision D0 or D1? Which is a better decision and why? Anyone? See, here we're quantifying what is risk. So we would want to take a decision where we can still get a good behavior, and we can say what good behavior is in terms of the average outcome. So if the decision that was taken was D0, well, the average outcome is just going to be 1 cake. There's nothing more to that. But if the decision taken was D1, the average outcome could be 3 cakes times the probability, then 0 cakes times the probability of that, which gives us 2 cakes. So since 2 is greater than 1, we can say that decision D1 is better than decision D0. And to make this statement, we just used the average outcomes, or if we want to write it formally, average over whatever is causing the randomness, which is going to be W in our case. Okay, now this scenario is very simple. What if instead of this we scaled the values? If instead of paying 100 rupees to get one cake, it was scaled to get, it was scaled to say paying 1 crore to get one house. Exactly the same as above, just scaling everything. The lottery again requires the same amount, and you could get 3 houses or you'd get 0 houses. In this case, which is the better decision? Is it better to just buy the house directly or to enter the lottery? In the previous case, clearly it was better to enter the lottery, because better is what we defined using average outcomes. Here, if we go by the same logic, it's better to enter the lottery. But intuitively, most people would not be okay with that, given the fact that the payment amount is quite huge and there is a finite probability of not getting anything in return whatsoever. So in such a scenario, what is typically being done is the worst case outcome is considered. That tells us a way to handle the risk in the problem, and that refers to this quantity. So what is this? This refers to the outcome for decision D and the state W. We take the minimum for a given D, for a given decision, and then of the different decisions, we take the one which has the maximum D value. In our example, both the examples are same, so it's the same numbers and I'm not that bothered about it. In our example, this means we know F can take 3 values, either 0, 1 or 3. For decision number 1, decision D0, there's only one option. But for decision D1, there are 2 options and we are supposed to choose the minimum of them, which means this is 1 if the decision is D0, and the maximum of 2 gives us 1. And this is the worst case outcome. And this outcome is telling that the right decision is to not get into the lottery. And there's one more possibility. There might be people who are still okay and who are not bothered about risk at all and would want to make their decision where they have the best possibility of getting the biggest reward. If that is the case, then that is typically called as the best case scenario. There, instead of choosing the minimum of the outcomes given a decision, it is first choosing the maximum and then choosing the decision that gives the maximum outcome. So in our example, this refers to, is anyone gonna try and answer this? This is fairly straightforward, right?
The optimistic approach.
Yeah. So if the optimistic approach was taken, this value would turn out to be 3, and D star would be D1. Just 1 second. So we saw that it depends which approach is being used to say which one is better than the other one. The approach defines whether we're going to get which particular decision is going to be the most optimal decision in the scenario. This is definitely one way to go about it. If from the very beginning we know what is the space of outcomes, what is the space of decisions available, and we are interested in only one type of behavior, that maybe we're just interested in optimizing and getting the best behavior every single time, then it's straightforward. But if there is a possibility of risk and we want to minimize that and at the same time come up with the best possible outcome, then we need to do a little bit more. Which means these three scenarios, these three different approaches, even though are different, can be clubbed together in one particular framework, and that's the next part we'll see. Yeah, you can ask your question now.
Yeah, in economics, we have this maximize the minimum loss or minimize your maximum profit. Or sorry, opposite, like some these rules are there. Are these connected with these approaches or they are different? Because there we talk about pessimistic and optimistic approaches, maximum loss, and we try to minimize the expected maximum loss.
So I cannot answer if it matches economics, as I'm not a economics person and I don't have much knowledge. But this much I can answer. This type of min-max behavior, this is very commonly observed in game theory also, in simple games like zero-sum game and so on.
Yeah, correct. Because for convex cases, both will be same.
Yeah.
Yeah.
So those cases are there, but what it is referring to, I am not aware. I can try answering next time, but I don't know right away.
Yeah, it's okay. Just question came up because the patterns is same.
This I'm assuming what you're saying should be correct, but yeah, it won't make any strong statements as of yet. But this is for sure. This type of things we see in game theory come up very often. This is the kind of behavior. This is trying to avoid risk, the worst case outcomes. This happens in games also, so should be the same in economics as well. All right. Anyone else? Any more questions? Okay, let me continue then. So now, like I said, it depends on what we are using to give the preference between two different decisions. That choice determines everything. Now, there is a standard theory to deal with such a situation, and that is called expected utility theory. As a part of that theory, they say that there is a probability distribution on outcomes, and it is defined in the following way. So it refers to, given a decision, it refers to all the state of the world for which the outcome is equal to some OI. So it's for a given decision, we are looking at what kind of outcomes we can get. Meaning, if we go back to our previous example, if our decision was D0, then there was just one outcome possible. That outcome was getting one cake. And since we were going to get one cake with certainty, the probability would just be 1. On the other hand, if we were talking about the other decision, there is a probability distribution. So O is referring to the number of cakes here. So if the number of cakes are 3, that would have come with a probability of 2/3 and probability of 1/3, we would have gotten 0 cakes. So this, what we saw in what was called as lottery earlier, is the same principle that is useful even further on. And this gives us probability distribution on outcomes. Now, under this expected utility theory, under some assumptions, they say that there exists the function u, which takes in the input of outcomes and gives us a real number. And this is such that the preference ordering between decisions d1, d2 would tell us the same preference ordering between the probability distributions on those outcomes, given the decision taken is either d1 or d2. And this is related to expectation of this utility function on the set of outcomes, on the particular outcomes, given the decision is d1 or the decision is d2. And these are all if and only if conditions. So now let's take an example to understand this a little better. So for example, it's a simple investment example. Again, the numbers are exactly same as the lecture notes itself. Yes.
This question is actually disturbing me a lot, and I wanted to ask in the group also. If you go up, you were talking about the PDs. Okay, now I don't know, I'm just somehow feeling we are force fitting conditional probabilities to decision. Okay, I'll tell you my reasoning. What if you go with a joint probability of your states and decision, like P of d comma omega comma d, and then you define, because now I'm missing many possibilities. Like technically I should have 6 possibilities because omegas are 3 and d's are 2. Some are not possible, so I can assign 0 probability. But why are we going with a conditional? Like, because fundamental quantity will be joint distribution. I can derive conditional distribution from this. If I know probability of d, I can derive it. Like, I don't know, maybe I may wrong, but I just had this question. Why are we starting with conditional probabilities?
See, the reason we're starting with conditional is, one reason is we can always write the joint this way, right?
Yeah,
and
it
here
is known.
choosing which decision to pick
Yes.
is something that we are controlling, or
Correct.
it's something that's controlled by the agents. Yes.
That is my confusion, because if that's the case, still it's a random variable, because every person will choose a different decision. So if I treat that, I can probability of w comma omega d comma omega make more sense to me than conditional directly. Like, I don't know, I just have a very deep pain in that. Like, I wanted to share when his chat was I was reading this in the lecture. I like why sir is going with conditional. He could have tried with joint and define joint, because both are random variable, agents are different, humans are different, decision will be different.
Okay, so one reasoning I can give as to why conditional is enough and we don't need to define joint is because choosing a decision is something that is to be done by us, and we are actually trying to optimize which decision to choose, right? That's why we have some preference ordering on decisions and so on. Meaning, there won't be a situation where we would be choosing between a set of decisions. We could randomize over a set of decisions, but we are still looking for optimized the decisions that will give us some optimal values. Since that is our ultimate aim, it doesn't matter if we look at the distribution from which D is being chosen. Right? This prior doesn't have much meaning for our control problem that we're trying to solve, or the minimizing the optimal problem that we're trying to solve. That's why it's okay to not worry about this and only focus on the conditional distribution here.
Okay, I don't know am I making sense or not, but it's only problem specific. But I can, as an independent developer, I can go with w comma omega. Suppose I want to design an algorithm, I can still go with d comma omega with my past data of d. I can define probability of d and then go. Is it okay?
Sure.
No,
that is okay, because you'll be ultimately doing exactly what is written over here, right?
Yeah,
This is exactly what you'll do.
Same.
That's fine.
I'm just like construct of a understanding. I'm questioning that like we can go with the joint and then come up with the same P omega D. It will be
We
same
can.
only.
It'll be same. It's just that it doesn't seem useful. That's
For me, it's like we are missing more information. Like something is missing there.
sure, this information is not there, but this information is not actually valuable. The decision is chosen by a third entity or like the agents. The choice will be one among the best or maybe a combination among the best, but that will ultimately give us the same optimal value, so it doesn't matter. So a distribution on that gives us no more information about the control problem. If we change the problem statement, then it could be of use, but typically it's not that useful.
Okay.
Okay,
Thank you.
let's move forward. Anyone else? Any questions? Alright, so this is the example we were looking at. This is an example where we have a capital of $1 and there are two investment options. One is A, another is B. In the first one, the outcome would have been $1.5 with with probability 1. If the investment that was chosen was B, then with probability half, we'd get the outcome as $3, else we'll get the outcome as $1. Meaning the space of outcomes is something that is ranging from, was it 0 in the original one? Okay, it's ranging from 0 to 3. Sorry, I think this is a typo. Okay, so here we're saying the decision is fraction of the capital that is put in investment A. The remaining, that will be 1 minus D, will be put in B. If that is how we go about it, then the actual outcome of this problem would be, with D fraction, we'd be investing in A, which gives a return of 1.5. And the remaining of the capital, 1 minus D, will be invested in B. And what we get there depends on which state of the world we are in, whether we are in W1 or W2. So if we are in W1, else we are in W2. Now we can repeat the same process as before. We can look at the various approaches of preference ordering. So one of them was average outcome. So if you try to take the average outcome from here, what value of D makes the most sense? I forgot. The set of all decisions, capital D, lies between 0 and 1. Okay, so here the average outcome would be, since the probabilities of these two states of the world are same, the average outcome would be just taking any of these outcomes and the probability of getting that particular state, this outcome and the probability of getting this state. So that is so if we do this, which is the correct outcome? We're interested in maximizing, right? So this is what you're trying to maximize, and we're maximizing over D. So if we simplify this, and since we're interested in maximizing, taking D to be 0 is the best possible scenario here. Which means, according to average outcome approach, it is best to invest only in B, meaning enter the lottery. On the other hand, if we were to use the approach of worst case scenario, then again we'll repeat the process. So now this is minimizing over W, meaning we're just supposed to minimize over these options. We're supposed to choose the option which is less, and clearly this is the minimum as compared to the above two, which means this is and here D equal to 1 is the scenario where we will get the best optimal behavior, and that means we would actually be investing all the capital only in A. There's another possibility now, like we saw that we can have some utility function giving us an idea for a preference relationship. If that's the idea we go with, we will need to choose. So okay, if we know exactly what our preference ordering is based on certain assumptions, if our preference ordering satisfies those assumptions, then there exists a unique utility function. But for now, let's just look at one particular example. So this is what we are trying to ultimately solve for, and what we are doing here is we are taking the expectations with respect to this omega or W. So this is the function's value for this, and one second, right, 3 times 1 minus D. This is for the other case. So this is for W2, this is for W1. I've written it the other way around. That's about it. Okay, so now let's say we're choosing the following as our utility function. Just notice this utility function differs from the one used in lectures by this factor of 2. So you can repeat the whole calculation for the one the way we did it in lectures here also. So the first thing that we want to confirm is whether this is concave and increasing or not, or for what values of alpha will it be concave and increasing. So to do that, we are interested in looking at the first derivative of this guy, and we want that to be greater than 0 all the time. So that is, the first derivative of this would be alpha minus 4x, and since we want it to be greater than 0 all the time, the range of our x or the outcomes is from 1 to 3, that means alpha needs to be greater than 4x, and it needs to be greater than the maximum of the value, means it needs to be greater than, it can also be equal, that is fine. That's our first condition. If this is satisfied, this is going to be increasing. And then we need to verify if this is concave or not. So to do that, we look at the second derivative. And we require the second derivative to be, ultimately it should saturate a little bit, as in the rate of increase should slowly decrease over time or over x. So this is, anyways, this is negative, so we're actually fine. So this is concave for every value, and for it to be increasing, alpha has to be greater than 12. Now let's do the following. Let's calculate the value of expected utility of the outcomes. Okay, so let me just copy from here. We can simplify this further. We know what is the form of u we have chosen here, the utility function that we have chosen here. We just plug that in, and we see that the same value comes up with the alpha in front of it. Adding the 2, we would get four minus d, and the next term would be the squared of both of these values. So the squared are so this is 1 plus 0.5d whole squared, and this one is 3 minus 1.5d. We simplify this further a little bit. So we'd get 1 and 3 square, that is 10. Then we get the squares of these two, 1.5 square and 0.5 square. They'll add up and give 2.5 t square. And the other term we'll get from here is plus t. From here we'll get minus 9d. Okay, and since we are interested in maximizing the utility with respect to d, all we have to do is take the derivative and simplify this. So this is minus alpha and equate this to 0, and this gives us the solution for the optimals. So now actually, according to this, so d is 16 minus alpha by 10. We know what values of d are allowed. D can only be in the range of 0 to 1. So as soon as alpha becomes more than 16, that's not feasible at all. And hence, for that, the optimal D star value has to be 0. So, ultimately, the optimal decision range is the following. And it depends on what values of alpha we are referring to. And on the other hand, remember, alpha has to be greater than or equal to 12, and here it has to be less than 16. So in this range, the decision is the following. So in some sense, this is telling us that the decision depends on which moment we are dealing with. If alpha is too large, that means we are in a situation where the first term, the linear term, dominates. And if the linear term dominates, the decision has to be just what would be suggested by the average outcome approach. And according to the average outcome approach, the best solution was to just invest in B. And that is what we are getting even from utility theory. On the other hand, if alpha is in a certain range, if alpha is such that it has the proper concave behavior and gives a decision that is in the feasible range, then there is a fractional value of D, a fractional value that is to be invested in A, and the remaining should be invested in B, meaning some amount of investment is done in both of them. And this is coming because of the second term. And the second term looks at the next moment. Clearly, we don't have to stop at just 2 moments and look at the utility function. There could have been more moments and same thing could be done. But analytically solving for those is a little tricky. So you can always use computational or numerical solvers for that. So far, okay? Any doubts, anyone?
In general, how many moments do we have in a utility?
It depends on the utility. So like if the utility has the form of a polynomial and the highest degree of the polynomial is where you'll stop. So that's the number of moments you have.
Okay.
On the other hand, on the other hand, if you have something like if you have something like exponential or log or under root x or that kind of a utility, then it's just basically saying you can take more and more derivatives, and all of those terms are genuinely equally important, and hence all those moments will get considered directly or indirectly.
But actually, this log and exponential are infinite polynomial in disguise only, like Taylor series.
Exactly, that's why.
So, but for example, if we go with tan inverse or some other function, so the tan inverse may not valid because it's not concave.
We need it to be concave and increasing.
Yes, my mistake.
Yeah. So as long as it's concave and increasing, we're okay. We'll use it for as a utility function. Else we'll be a little skeptical. Typically, it has to be concave.
But increasing, like any increasing only these constant. But I don't know. I'm not convinced. Like why? Why are we only these two? What if it is convex and you go minimization of? That's also possible.
Convex and minimization is same as concave and maximization, right?
Yes. Got it.
Yeah.
Thank you.
Okay. So this is another example. How about I give you all like 2 minutes to try out this example on your own, and then I'll go on and solve it. Again, there is some investment between A and B. Capital is the same as before. The only thing that I've changed here is these numbers. These numbers are slightly changed, and the utility function is now exponential. It has the exponential form. Why don't you guys take a minute, think about how to approach this, and then maybe tell me your approach, and then let's try and do it together and make this a little more interactive.
That is 0, right? 4 and 0.
Yeah, that's 0. Oops. Yeah. Okay, let's try working it together. So what is the outcome f given d comma w? What is that here?
2d plus 4 1 minus t.
Yeah, so remember d is the same thing as before. It's the fraction. Let's say the fraction invested in a again. Same thing. We're not changing that part. So now, yeah, tell me.
4 minus 2d and 2d with half of probability.
4 minus
2d
and just 2d.
down 2d.
Yeah, that is correct. The first one, okay, let's write it like this. It is 2d plus 1 minus d, 4. What you said was correct as well. This is just so that it's more clearly visible. And each of them is with probability half. Okay, so now we're told to use this particular utility function. And we're supposed to take the expectation over w for this utility function. So that means we are doing the following. Yeah, so this was 4 minus 2d. Okay, this is just plugging in, nothing more than that. Then next, just like before, we'll be taking the derivative of this. We want to maximize, so we're taking the derivative with respect to d, because everything is like very clean and nice functions. You can take derivatives easily. So when we do that, this is as it is. Both of them have minus. I'm taking that outside. This is e to the power minus 2d minus 2. And this term will have 2 coming up here. That's the type. And we're supposed to equate this to 0 and solve for d. Solve for d and tell me, what do you get? Here, to solve for d, you can take the 2 common. Actually, you can say that this is equal to 2d. And this can only be true when d is 1. And d being 1 means all of the investment is in A. So this is similar to a worst case behavior, risk minimization in an extreme situation. The reason why this is becoming exactly the same as the worst case approach or risk minimizing is because in the problem, the expected outcome for B would have been $2, and that matches with A. So the preference ordering is actually the same. Because of that, it makes sense to just go for investment A itself, and why take the risk? The risk is not worth it because you'll not get much on average. On the other hand, if we were to change these probabilities, so if I were to change the lottery distribution, then I might get a different behavior here. So the point here is, even though I am using a utility function with infinite moment, exponentials have infinite moment, still what I'm getting is very similar to the worst case approach, just risk minimizing approach. So this can also happen. It depends on the distribution, it depends on the problem itself. This is the...
Yes, so I'll try to simulate this in MATLAB with different probability.
Yeah.
And then I'll try to see, but I'm like, okay, in my day-to-day activity in my work, sometimes I don't have utility in my hand. For example, I want to distribute a compute resource on my the various kind of hardware, and I want to choose how to distribute. Now in that scenario, same like similar to investment, I'm feeling it is same. D is equal to 0, 1, and I have two hardwares. I want to distribute my data to compute. In that case, I don't have utility there. So here I'm assuming utility is already present and well defined. Is it or any other, like I can take any utility?
So if you know what kind of preference ordering you have in mind, what kind of a relationship you have, what is the exact behavior, then there exists, so this is the theorem, then there exists a unique, well, up to a certain scenario, there exists a unique utility function. So it depends how you've chosen the preference ordering. If the preference ordering changes, meaning your objective of the problem changes, then the ordering will change, and hence the utility function for that captures the same minimization problem will be different.
Okay, so it
This
depends
is like a
upon me,
result
like, how
given
do I
to
choose
us.
utility?
Sorry, come again.
It depends upon me, how do I choose utility?
It depends how you choose your preference ordering.
Preference ordering.
What can you choose in your preference ordering? That, so according to this theorem, there is a unique, or there's a set of unique utility functions. If that is the case, then you're just saying that for your preference ordering, you have a way to choose between a set of decisions, to order between decisions or order between the probabilities on the outcomes. And that is the same as taking the ordering on the utility function also, the expected value of the utility function.
Okay.
Okay. That's why I'm showing a few different examples of utility functions. Different behaviors can be captured using different utility function. Now, which one to choose in which scenario and which is more meaningful, all of that actually is studied in expected utility theory. We are just using one of their theorems to make the rest of our points so far. Okay, I'll continue if there are no more doubts. Alright. So like he has asked, is U unique or can you choose any utility function or U? Now, if our preference ordering or if our probability distribution or what we are calling as lottery satisfies a certain assumptions, then it is said that the U that will come out of it, given a particular preference ordering, has to be unique. Okay, so let's go through those assumptions one more time. These were covered in the lecture. If you are comfortable with it, I can skip this. Else, we'll go through it again. Any preference on this? Okay, let's quickly go through it then. If you have doubts, you can ask. So, this curly P refers to all the set of lotteries. By lotteries, I mean the probability distribution on outcomes, or what was written earlier in this notation. P, D of some outcome O. or maybe OI if that is more comfortable. The set of all of these lotteries is denoted by this curly P. So now if we have, say, two lotteries, P1 and P2, from the same set, then a convex combination of those two lotteries. Convex combination meaning you've taken some alpha amount of P1 and some 1 minus alpha amount of the other one, where alpha is restricted between 0 and 1. Then what you're doing is you're thinking of P1, P2 in the probability space, okay, as just 2 points, and your alpha allows you to join the line segment between them, and the value of alpha will give you one of those probability distribution between them, and that is what they are calling as a new lottery. And what this new lottery means is, let's say this lottery is on some outcome theta j, then that is the same as saying with alpha probability I am choosing lottery P1, and with 1 minus alpha probability I'm choosing the other lottery. This is the definition. This is what it means to take a mixture or take a convex combination of two lotteries or two distributions. Okay, so this is the setup. This is what we're referring to, the set of lotteries. Now these lotteries have to satisfy a few relations. So the relations are mostly related to preference orderings. So to have some preference orderings, we will have preference ordering between two objects first. So there's one P1 and there's P2. So there are a few different possibilities. If we were making a preference in normal objects, some scalars or actually scalars only, then we'd be either talking about equality or inequality, or maybe strict inequality. That's the same thing here. It's just denoted in a different way. The first symbol, this one, refers to equality, as in there's no preference on the other. Both are equally preferable. That means, according to this, P2 is more preferable than P1, and at the same time, P1 is more preferable than P2, meaning both are equally preferable. So this is another option is, this was option 1. Another option is there is a preference between the two. One is preferred over the other, which is like saying P2 is preferred over P1, but it never does happen that P1 and P2 are equally preferred, meaning P2 is always preferred over P1. So this is always preferred. So these three together, they form a complete set of relations of preference between two lotteries. Another thing is, if they satisfy this, they should be transitive also. Transitive means if P2 is preferred over P1 and P3 is preferred over P2, that means P3 is preferred over P1, which is this. So this type of transitive relation is also present. So this is assumption number 1. If the set of lotteries has this property, then we can talk about other things. Is that okay? Alright, the next assumption is if P1 and P2 are equally preferred, then, so what this one is now trying to say is, suppose we take some P from the same set of lotteries and choose P1 versus P2. Just like before, we can talk about convex combinations, right? So if we restrict ourselves to same alpha, then since P1 and P2 are the same, or that they are equally preferred, the resultant will also be equally preferred. This is what second assumption is saying. Meaning mixing is not changing the equal preferencing for now. If we look at the second one, this is saying mixing is actually not even changing the always preferred scenario also. Is that okay? Or any questions, anyone? Alright. Now fourth one is between 3. There is a preference relationship between 3 lotteries, and let's say it's in this order. So let's put it this way. So there's P1, there's P3, and there's P2. Then it says that if we were to just take the convex combination of P1 and P3, so this is just preference ordering. Preference ordering is what I'm denoting over along this horizontal line. So this is the same as taking a mixture between P1 and P2 for a particular value of alpha. So there exists some alpha between them. Such that we can find a P, let's denote it by P alpha, which will be such that it will match in preference ordering with P2. So this P alpha, which is alpha times P1 plus 1 minus alpha times P2. So that's a convex combination of P1 and P3. These are the two extremes, right? The least preferred and the most preferred. So a convex combination of those allows us to find a P alpha which is equally preferred to P2, which we knew was somewhere in between as far as preference goes between P1 and P3. So the theorem says if there exists some preference ordering between the lotteries such that all of these four assumptions are satisfied, then there exists a function, a real valued function, which takes an outcome and gives us a real value such that for all P1, P2, for all P1, P2 pairs from the set of lotteries, preference order between P1, P2, for example, if P2 was preferred over P1, would be the same as expectation of the utility function with respect to P2 will always be greater than probability, the expectation of P1, expected utility with respect to P1. Meaning the preference relation here is translated into an optimization problem in the space of utility functions, or the expected value of that. This is what this theorem is saying. So if we know what that U is, what that correct utility function is, that captures the preference ordering that is of interest to us, then we have a straightforward mapping between the two. Okay, any questions?
Yeah, I have some confusions here. Okay, so these are all axioms. We'll
Yes.
start with this. But here we are dealing with a P, that P is a conditional probability of omega given D.
Yeah.
So D decision is already taken and omega state has arrived. Or maybe it's a random condition. So the distribution of omega given that your decision has taken. My question is, here when I choose P1 and P2, I prefer when I apply, which means decision is already decided and I'm preferring on a state of the world or environment or maybe the capital omega. And but when you talk about the expected utility, same D is considered or it's a set of D. Like for
Same D.
example, this theorem is valid for individual decision or it's a set of decision.
Individual. So remember how we were calculating these expectation values. So this P1 basically refers to P of some D1 and whatever outcome space that it was referring to, versus P2 refers to some P for a decision D2. And correspondingly, their utilities will have a form like this. So it's U of F D1 omega, whatever that omega is. Omega is where the randomness is, given that we've already taken decision D1.
Okay. Okay, so that was my confusion. Now it's clear. So basically, P1, P2 are two different decisions, and inside P1, the distributions that axis will be states.
Sorry, come again?
I was confused with it. Now it's clear. But
Okay.
my clarity is like the P1, P2, and P3, and so on. Those are decision-based probability distribution on states.
On outcomes.
On
Remember,
outcomes. So
the lottery was defined in the following way. Where is our definition? Sorry. Yeah. These are probability distribution on outcomes.
on outcome.
This is what it is on.
Okay. On all possible outcomes.
Yeah, on possible outcomes that are reachable once you've taken the following decision.
Okay. Okay.
Right? With each decision, you can't reach all the possible outcomes. You can reach only a fixed set of outcomes. So whichever ones are reachable, you'll have a distribution on top of them.
Perfect. And so, just as I'm curious, suppose I want to try with instead of conditional, I want to try the joint of this comma D with the same preference I'll make. Is that same? I need to check. I'll check it out by
Yeah.
how they divide this, and I'll try to do with a joint also.
Okay. Let me know how that goes, okay?
Yeah.
All right. Now we're coming. So far we've been talking about risk and what are the different approaches that can be used to handle risk in the definition of utility function itself. The other aspect that is equally important in stochastic control is of information, as in what is known to which agent. So I'll take a quick recap of the problem that was done in class, and if you have questions you can ask here or later on, and then I'll take one more scenario. Okay, so in class this was the scenario taken. So this is a linear system. Here the x1 x2s are the states, and this u0 or u1 are like the decisions or the control parameters, and this w0, that is some random variable, and we've taken it to be such that it takes the value half or 1 or minus 1 with probability half. And you can see there's like a sequential behavior here. So you can think of the sequential behavior roughly as follows. So some w0 value is created by nature. It goes in some black box that ultimately adds them and calculates x1 for us. And to do that, it requires the control or the action u1. Using all of that, it has created x1, and now this x1 is used by the next guy. And here again some action needs to be taken, which is u1. So let's say in such a problem, in such a sequential problem, the goal is to find u0 u1 so that we can minimize the following expectation. Now here the only randomness is in w0, so that's what the expectation will be over, and we're looking at the absolute value of x2. So this is what you're ultimately calculating. Now in the first setting in this problem, we're assuming that the choice of u0 and u1 is done in the game. It's done sequentially, but it is at this time the agents know nothing. So like this agent doesn't know what is the value of x1 or u1 or w0. It doesn't know any of that. It just has to take an action. It doesn't have information. That's the kind of scenario it is. When that is the kind of scenario, then it was shown in the notes that the minimum expectation of absolute value of x2 turns out to be 1. And this can happen when u0 plus u1 was within the range of 1 to minus 1. Does anyone have any doubts on this part, or shall I move on? Okay. Okay, this much I'll do. Rest I'll leave for you to try out on your own. Okay, so this expectation is the same as x2 depends on x1 and u1, and x1 depends on u0 and w0. So if I write all of that, this means x2 is and this is the same as, remember the expectation is over w. That is the only random variable here. That's the cause of uncertainty. So there are two possible values w can take. It's plus 1 or minus 1, and each is with same probability. So this is now it's the distance that's supposed to be added, and you can check this out. You can make simple drawings of this kind. This is where the mod u0 plus u1 lies. Then adding 1 to it gives you a certain distance, and subtracting 1 from it will give you a certain distance. And ultimately here what you're doing is taking the sum of these two distances, or rather the average of those two. If u1 and u2 lies between minus 1 and 1, we can see that the minimum that they can do is if u0 plus u1 was itself equal to 0, and hence the minimum value of this expectation will be 1. On the other hand, if u1 plus u2 is anywhere else, if it's on this side or this side, then the distances will increase, and hence the sum has to be more and will not get the optimal value in that region. So this was the argument for case 1, where u1, u0, all of these were chosen sequentially, but nothing was known. So now let's see what happens if some information was known, in the sense I made a error. Here u1, u0 and u1 are chosen at the same time. They're not chosen sequentially. That is the reason why nothing is known. On the other hand, if they're chosen sequentially, means u0 was chosen earlier, w0 was already realized, x1 was already realized, and that x1 realized value would be known at this level. And if the value of x1 is known at this level, meaning u1 can now just be a function of x1. It doesn't need to bother with what is w0 and what is u0. And since that can happen, this minimization over u0, u1 actually reduces to just a minimization over u1, no matter what u0 is chosen. So u0 can be any scalar value. After that, x1 will get a realized value, and that when added with u1 is our x2. And now u1 can just be a function of x1, so u1 can be minus x1. When that happens, this will actually be, not maximize, minimize. That will actually be the minimum value, which is 0. Now notice what happened here. When there was no information, when it was case 1, the expectation value that we got, whatever was our goal, what we were trying to minimize, was 1. But on the other hand, when we had some information, and that information was specific, okay, u1 was realized, x1 was realized. So before u1 was decided, agent knew what is the value of x1. And after that, u1 was chosen, meaning u1 was dependent, could be dependent on x1. And because of that, what we got was 0. We managed to minimize it even more. So what this is showing is, if the right amount of, or the correct information is available, optimal problems, the problems can be optimized even further. This is what this example is showing. Now I'll show you another example where, even though some information, something more is known, it doesn't really help. So let's take another example. Now this is my example. Again, x1 is something that depends on w1 and u0. Same thing as before. x1, x2 are the states. u1, u2 are the decisions or the control parameters. w0 and w1 both are random variables. How I'm defining those random variables is gonna come up next. So the difference between this problem and the previous one is, previous one did not have a w1. That's it. The rest is the same. Okay, so now if a scenario is like this, and we are trying to minimize the absolute value of x2, we have to understand the expectation in this case is not just over w0, it's over w0 and w1. And the minimizing, we are minimizing over u0 and u1. So this is our problem. This is what we are trying to minimize. This is our goal. Now, for this particular example, even though I've taken w0 and w1, I've taken w0 to be a constant. So it's just, it has value 1 with probability 1. So it's not actually a random variable, but w1 is still a random variable. So at the level of, at the first x1 input level, it's just some constant value that got in, and there's a controller, or there is a decision to be made. There's no more randomness there. There's just a decision to be made. On the other hand, at the level of x2, there is some amount of randomness. And obviously at the same time, there's a decision to be made. So let's try and see what happens here. Since W0 is a constant, I am not worried about taking the expectation over W0 in this particular example. So the expectation is only over W1. Now, this means okay, let's write it out like this. So x2 is W0 plus U0 plus U1 and W1. We know the exact value of W0, so we can plug that in here.
This is coming same distance between 0 and -2.
Yeah. Earlier the distance was between -1 and 1. Now it's between 0 and 2. Correct. So you're doing it right. So like he said, like Abhay said, this would be half U0 plus U1 plus 2 and U0 plus U1 and nothing added. 1 minus 1 will get cancelled. That's why it is like this. So now if you try and minimize this, what values or what will be the minimum value that you get? Same logic as before. Nothing has changed here. Okay, so we need the range, right? So let's look at the range of U1, U2 where it's meaningful. So the easiest case could be when U1, U2 are both, sorry, U0 and U1 are, the sum of those is greater than or equal to 0. When that happens, the minimum of this expectation would just be 2 by 2, which is just 1.
Actually, -2 to 0, right? Is it a distance? This is the case where distance from 0 and -2. Because you have +2, right? U0 plus U1.
Yeah, correct.
So the range will be -2 to 0, right? So you have mentioned is greater than 0.
Oh, sorry. Right. So it will be like this, right? The distance is 0. So if U is somewhere over here, correct. So in this range, the minimum value will turn out to be 1. In any other range, meaning if U0 plus U1 was outside of this range, then the minimum value will not be this. As in, this will not be the minimum reachable. So it's only in this range that we can say the minimum reachable is 1. So the minimum is still the same as previous one, even though this is a slightly different problem. Okay. Now here, just like previously, we did not use any extra information. X1 was not known to you. X1 was not known at the time of choosing U1. That's why both are chosen at the same time, and it's the sum of those two should be in a certain range. That's the kind of result that we get. Now, just like previously, now if U1 and U2 are chosen sequentially, or that there is some information gathering that's happening, meaning X1 is something that is known at the time of choosing U1, then what happens? But remember, here there is a random variable also, and we are assuming that this W1 is not known at the time of choosing U1. So W1 is still a random value that will just come into the whole picture. So we're supposed to repeat the whole process and see, is the expectation value of X2 same as previous or different from the previous case now. So just like before, we can say X2 is X1 plus U1 plus the extra term. Now W1 can take value of 1 or minus 1. It doesn't make sense for U1 to try and guess what value would be chosen by W1. So it will end up just being something that depends on X1 itself. So if we say U1 is just minus X1, in that case this reduces to expectation over W1, which will turn out to be 1. And you can verify that this is the least it can do. You can verify this more formally and check that the minimum of the expectation of absolute of X2 will turn out to be 1. So now in this example, what happened was there were two factors. One, like pointed out in the beginning, we added something random in the state that we are actually measuring at the last. Like in the target level, we have some amount of randomness, and this randomness is not captured or not taken into account into X1. Even though X1 is known, since W1 is not known, U1 is still restricted. U1 still has to deal with the randomness in the problem. And because of that, even though U1 is chosen after knowing X1, it still is not able to perform any better. The control is no better. And the point that I'm trying to make here is, sometimes enough information might not be enough to give us this type of a situation where the control improves or the optimal value improves. Okay, so today we saw the role of risk, different approaches to handle risk, and the role of information in stochastic control. There were one or two more topics discussed in the lectures that I've not talked about so far. One of them is Arrow-Pratt's risk measure. This one, let's say you're talking about a utility u of x, then this Arrow-Pratt's risk measure is just the second derivative with respect to x only, second derivative of the utility function divided by the first derivative. This is a measure of risk, as in how risky is a particular decision used in the form of expected utility. And you'll see in the assignment there is at least 1 or 2 questions which ask you to calculate this. So you just have to plug it in and solve it. It's quite straightforward. Another topic that is covered is risk aversion, or how do we say if the utility function that is being chosen is risk averse or not, or if the decision that is being chosen, given that we have already decided on our utility function, is that risk averse or not. So for that, it's the Jensen's inequality. I'm again writing it in this form. U of x means x here refers to the outcomes, okay? So this expectation is less than or equal to the outcomes directly. Remember, one of you were asking, why does u have to be concave? This property is satisfied by concave functions. If u is concave, then this property will be satisfied. This is called Jensen's inequality. Okay, with this I have covered all the things that I wanted to cover. Now we can take any questions that you have from what I covered today or from the lectures.
This thing, the risk averse equation,
Mm-hmm.
it's by default a property of concave function. So why are we telling this is a risk averse? Because if I am taking utility function as a concave, this property will hold at any time. Like for any probability distribution, it will hold.
Yeah. That's like 2 different ways of saying the same thing. So okay, let me put this equation in words. So here, this side I'm taking the expectation
Of utility.
of the utility.
The utility of the average outcome, that is fine, understood. Like,
But
okay,
this is okay.
input
Let me
question.
finish. Give me a minute. This
Yes,
one is calculating the utility of the average outcome. Here, the average outcome that we are referring to will occur with probability 1, meaning that average outcome will occur. That is what is captured by this inequality. Meaning, even if we take a risky decision, we will at least get as much as we would have gotten from the expected utility itself. That is why any particular decision which satisfies this condition is making sure that the risk is as less as possible.
Okay, so in your statement, when you say average this, the expectation inside, the probability P, and that side also same probability distribution, right?
Yeah, so you'll be taking the probability with respect to whatever decision, right? So if I were to, okay, let's say if I were to write this more cleanly, I would write it like this. So this is UF D1W, okay? Similarly, this is of U. But this is for the particular decision D1, okay? And
Correct.
this is expected.
X,
So now the outcomes that I'm referring to are the functions f of D So the D is again D1, and whatever are the state of the world for that particular decision, that's the expectation over.
Yeah, correct. But question is something else.
Yeah.
I'm asking that whatever it's a property of a function chosen by maybe developer or algorithm designer, or maybe person who designing you or choosing you, a preference. It's nothing to do with risk, right? Still the question holds exactly valid. I'm just simply asking. This is a property of function. Okay.
You're referring to U here, the function
Yes,
U?
yes, yes,
Okay, yeah,
yes.
continue.
Yeah. It's a property of a function. So there's nothing to do with risk ever. For example, somebody choose P of D2 and D3, still this inequality will hold, right? Still, even I'm somehow not getting it. Why are we calling this risk ever? For example, in your example, 1 minus e to the power minus x. Okay, any value you choose in x in a particular domain, this inequality will hold. It will never cross. It will just make more and more equality if you go to higher values of x. So I'm thinking, like, how come some risk aversion is happening here? Like, if you plot this function 1 minus e to the power minus x, it's a concave function, right?
Yeah.
So at any point, if you choose a particular interval x, which valid for this function, in that this inequality will hold always. So there is nothing in that function to take risk. It's like all values, all are risk covers. All points are risk covers. There is nothing risky points. Like basically, I'm thinking in this statement, how do I use it for risk thing? I don't know.
Yeah,
I'm
this
making
is
sense
okay.
or
So
not.
this is okay. So let me clarify. This statement about risk aversion is saying that a utility function is risk averse. You recall this particular example, right?
Okay. So the choice of function is risk
Yeah,
covers,
it's the
not
choice
the
that
x value.
we saw this in our example happening like very naturally. It's the choice of utility function that ended up giving us a value of d which is actually the same as the worst case scenario, and we know worst case scenario does refer to like making sure we're taking the minimum risk possible. So in that sense it is risk aversion. It's the
Okay.
utility function that makes our approach risk averse.
Okay. Then, if that's the case, I know that I can choose any concave function. So means concavity definition itself is my risk aversion.
Yeah.
Perfect. Now I got it. I got the clear picture.
Okay.
This is about this function. So I can make this second derivative, negative, all this property as a risk averse for the utility function. Yeah. Thank you so much.
Yeah, sure. Okay. So so let me just take some 5 more minutes or so and quickly revise what we talked about today. If anyone has any doubts, you can still ask. So we talked about what is risk. We looked at the formal model and we looked at an example. This was the example of cakes, whether to enter the lottery or just buy the cake directly. And we saw that if we are okay at times to not get any cake at all, we should go for the lottery. And since to enter a lottery all we had to pay was just 100 rupees, it was fine because we used the average outcomes, the expectation over outcomes as our choice to decide our preference. So we got to know that it's okay to choose the lottery, but at the same time, if it's the same problem just scaled up, instead of 100, if we were to pay more and the entry to the lottery was more, maybe like 1 crore, and the output was houses, then the possibility of losing all of that money in the lottery and not getting anything in return and ending up that being happening with a finite probability, and in fact a good enough probability, then that's a risky decision. That's what our intuition also says. But this means to capture a risky decision we need more definitions of how to come up with preference orderings, or what kind of approach should we use to capture this idea. One of those things was the worst outcome. which is basically saying that we looked at, given a D, we looked at the minimum output possible for the range of W's for that D, and then once we have chosen those minimum, we maximize over the D's. We choose the D that gives us the maximum of the worst options available, and that will end up being risk averse, or that will end up making sure risk is minimized. So in this particular example, it would tell us to not enter the lottery. That is, if somebody is scared to lose money, they would want to make sure that the chances of them losing all of it is as less as possible. They'd in fact not enter in a situation like this. The other extreme case is if somebody is completely okay losing any amount of money, but they want the best possibility. They want to be able to get the best possible outcome. In that case, it is maximizing over the W's and maximizing over the decision D. And that ends up giving, in this particular example, a situation where the decision should be to enter the lottery. Then we saw that to capture all of this in a more formal setup, we use a conditional distribution, and the condition is on the decision. So given a decision D, this is the probability distribution over the outcomes of value U0. So for any particular decision, for example in the previous one, whether to enter the lottery or not, so let's say not entering the lottery, then there was only one outcome possible, so that will get a probability distribution on it. If there were more than one outcome possible given a decision, then there'll be a distribution on those. With this probability, we'll get this output and the other one, so on and so on. This is what we've been referring to as lottery so far, or the probability on outcomes. Notice this is a conditional probability on the decision. It's only when you have chosen a decision that you can pick the D in this FD, and then you're just varying over W's. And whichever W gives you the particular outputs, those are the ones you're clubbing together and you're writing it. Next, we saw that the formal way of looking at these things comes under expected utility theory, and which says that under some assumptions, there exists a function U which takes in the outcome as the input and gives us a real number. This real number gives us an ordering between two preferences or two decisions. And what this is ultimately saying is, if there is a preference between the decisions, that means there is a preference between their corresponding lotteries also, or their corresponding probability distributions on the outcomes. And if there is a preference ordering here, that means there is a preference ordering, in fact an inequality between the expected values of the utility at each of the outcome values possible. Okay, and to understand this, like to understand the role of the utility function, we saw a few examples. So we saw this particular example, same as the textbook, same as the lecture notes, and we used a different utility function here, and that helped us understand what is the meaning of how to get a concave function and increasing function, like what kind of restrictions are there. Then we saw how to go through and calculate the expectation over these utility functions and maximize them. This maximization ultimately shows two things to us. One, the choice of utility function tells us how much information is there. Is it just first order information, or first information equivalent to first moment, which is just average of the outcome, so just this component, or there is information which is dependent on risk factor also, so there is some amount of risk but not much, something of that sort. Then we saw another example where the utility function that we chose was a different one. instead of a polynomial utility function, we chose an exponential one. And in this particular example, we saw that the optimal decision ends up being the same as what we would have gotten from worst case. Meaning, even though this utility function has information about all the moments, it's still focusing only on the worst case scenario, or it's the same as having information about the risk factor, the worst case scenario, the worst outcome. Next, we recapped the assumptions that were required for the assumptions on the preference ordering that were required for this particular theorem, that says that if these assumptions are satisfied, then there exists a utility function which allows this type of a preference ordering, that if there is a preference ordering between two decisions, the probabilities of the probability distribution on outcomes given decisions, then there is a preference ordering even in the expectation values, and vice versa. So it's a if and only if condition. And last, we saw the role of information in all of this. So this is a sequential type problem, and this is a rough diagram to depict the same problem. Here x1, x2 are the states, u0, u1 are the decisions, w0 is a random variable. So for this problem, we saw if u0 and u1 are chosen at the same time, meaning at the end of the whole scenario, meaning neither of these realized values are known to anyone. They're choosing the decisions without information. Then the minimum expectation over the absolute x2 ends up being 1. On the other hand, if they had some information, as in if u1 was chosen, u1 and u2, u0 and u1 are chosen sequentially, meaning u0 is chosen and hence x1 is realized and known to the other agent, and u1 is chosen after knowing that, then it helps and the optimal value actually reduces. So there's a difference in the optimal value in the two scenarios with gain of information. On the other hand, it can still happen, we saw in this particular example, that even with extra information, see, this is scenario 1, no information, scenario 2 with information, the optimal value could still be the same, meaning there is a possibility that information doesn't gain anything. And with this, we have covered most of the topics from week 1's lectures. And next week, it's going to be a formal introduction to Markov decision process and the next required things to talk about optimality and so on. All right. Any questions from anyone? Okay, if no questions, then we can end our session here. Thank you so much for joining. I'll hang up now, okay?
Thank you.
Yeah, thank you. Bye-bye.